Alright, so quickly to review, we started our unit off talking about solutions to differential equations. Alright, solutions to differential equations. And to find those solutions, we had to take the antiderivative of a function. So we said, by definition, if we have a function little f, and we take the integral of it, or the antiderivative of it, we get a solution, big F, okay? And that is a solution to the differential equation, or a solution to the integral. But there are infinite numbers of possible solutions if we just add a constant, okay? And when we add that constant, we now have this whole thing together is what we call our general solution, and we gave that the label big G of x, okay? So that's a general solution. Now the truth is, in real life, we're usually talking about one particular equation, not the general solution. So now we're going to talk about how to find those particular solution using initial conditions, okay? Initial conditions are going to be a value either a value of your function that will help narrow down the possibilities and help you solve for the constant c. Okay, so we know we have this form, f of x plus c is our general form. A lot of times, if we just have one point, we can solve for a particular solution. Okay, so let's take a look at example number 7. Okay. Here we're given big F prime, so the derivative of big F is 1 over x squared. We have a restricted domain of x greater than 0. We want to find the first the general solution and then the particular solution that satisfies this condition, that f of 1 equals 0. Another way to write it would be the point 1, 0, okay, satisfies. Whatever our final equation is, that's going to be one of the points that satisfies it, okay? So, first thing we need to do is use our integral notation to set up the problem, okay? And so as a reminder, if f prime is given, then if we take the integral, we're solving for big F. So big F equals the integral of 1 over x squared. So 1 over x squared, what's that called?
Power.
That's our
integration.
Integrand. That's our integrand. Okay, and then dx. What is x? That's our variable of integration. Okay, important to be familiar with those terms. Okay, all right. So now we have our integral set up. And now we can solve using our simple power rule we've talked about. So first I'll rewrite it. Integral of x to the negative 2 dx, and then of course our solution is in the form of x to the n plus 1 over n plus 1. So it's x to the negative 2 plus 1, which is negative 1, over negative 2 plus 1, which is negative 1, plus c. Okay, so we have a solution, and we know that that solution will work. The problem is it's too general. It is our general solution. All right, c could be any constant. And if you look at your book on page 247, it shows you all the possible solutions, and they all have the same shape. They just are shifted vertically. So that c, okay, is just a vertical shift in the graph. Okay, so to determine what graph or what equation is the actual solution, we need to go back to our initial condition. And remember, our initial condition is f of 1 equals 0. So if we plug in f of 1, negative 1 over 1 plus c, plus c equals 0. All right, now we can rearrange and solve for c. Negative 1 plus c equals 0, therefore c equals 1. Okay, we're still not quite finished because we haven't given our final answer, but I'll write it over here in the bottom left. F of x equals negative 1 over x plus 1. That's our final answer, okay? That is a particular solution. I'm going to abbreviate solution, okay? SOLN. All right, our particular solution, okay, that particular point is satisfied by this function, okay? Okay, so one place where this can be applied is in vertical motion problems, and these should be familiar from physics class. So if you are talking about the motion of a ball and how it moves with time, okay, you always get a sort of parabolic kind of curve. Using these, solving those ends up being just like solving our differential equations and using our given initial conditions to find particular solutions, especially when we start out with initial velocity, okay, and we want to find position. So in the past, we were given position and then took the derivative to find velocity, right? So differentiation, right? We're given s of t, and then we found s prime of t equals v of t, the speed, right? So now, with integrals, okay, now we can be given our speed, our v of t, and then go backwards to find our position function, okay? And then we'll get our position function plus a constant, and then if we're given some initial condition, like the initial height, then we can find the exact function, okay? So that's what we're going to do here. Okay, we start with a ball being thrown upward with initial velocity of 64 feet per second from an initial height of 80 feet. Okay, so the first thing we want to do is find the position function given, sorry, that's a typo, given the height s as a function, oh, sorry, no, that's right, read it wrong, okay. We want to give the height as a function of time, and then we want to find when does the ball hit the ground, which what does that mean in terms of speed, position, what does it mean when the ball hits the ground?
Position is 0.
That's it, when position s of t equals 0, okay, and it's not at t equals 0, it's at some time later, okay. All right, so first let's take a look at what our initial conditions are, okay? We know that the initial height is 80 feet. So that means that at time t equals what? It's 0, okay? The position is 80 feet. And we also know that the initial speed, so the derivative of time, the derivative of position at time equals 0 is 64 feet per second, okay? So those are our initial conditions. We also have to remember a very important piece of information, and that is that the acceleration, which is the second derivative, of a falling object in feet per second, feet squared per second, is 32. It's half of 16. You're going to see why right now. Or it's twice 16, sorry. Okay, because we start with 32, and I'm sorry, it's not just 32, it is going down.
Yes, 32, it's negative 32, what's the name?
Feet squared per second.
Yeah.
Okay. All right, so if we start with acceleration due to gravity, and find the integral. So we know that s double prime of t equals negative 32. And if we find the integral of both sides, And I'm going to show you kind of some extra steps here just to be clear. Find the integral of both sides. Finding the integral on the left side just means going back one. So we start with the second derivative. We're going to end up with the first derivative on the left side. And then on the right side, we're following the same rules we've been looking at. So it's just a constant. So what are we going to be left with? T plus c. Okay, good. So negative 32t plus c. This is our speed. Okay? This is our speed function. Now, we have to find what is c in order to complete this problem. And this is where our initial conditions up here come into play. Okay? So we know that v of 0 equals negative 32 times 0 plus c, and it equals 64. So c is 64. So our final speed function is negative 32t plus 64. Is that okay? Okay. Now, let's talk about where the 16 comes in, because that's only one step. We want to know what is the position function, not just the speed function. Okay? So we have to take it a step further and say we know that the derivative of t is negative 32t plus 64. We want to know the integral, right? dt, dt. Okay, so again, by definition, this means s of t, the position, is equal to the integral of this function. Well, what's the integral of this term? All right. Okay, so this is where the 1/2 of acceleration comes in. It's in this integral process. You end up with a 1/2 of 32, which is 16, which that's what's familiar to you. Okay, so s of t is negative 16t squared plus 64t plus c. And again, we go back to our initial condition. Now we're using our initial condition here. Okay, so s of 0, whoops, let me change colors. S of 0 is equal to negative 16 0 squared plus 64 times 0 plus c, which is equal to 80. So in this case, c is 80. Okay, so our final position function would be negative 16t squared plus 64t plus 80. Okay.
Do you have to know the speed like the equation of the speed?
The particular solution or the general solution, or just in general?
The major equation is like the what is that called?
Like the equation of motion?
Yeah.
You don't. You can derive it if you know this process. Okay. Remember, all we started with was a constant, negative 32.
Yeah.
And then we could derive it all the way from there.
That's why I'm like, how you get negative like 32 or 16 if you don't know the equation of the.
Okay, so if you have to know that negative 32, that the acceleration is negative 32 feet squared per second. But you can derive everything else using calculus. In physics class, they usually make you, usually make you memorize this kind of equation, 1/2 at squared plus v naught t plus s naught. Remember that? Okay, and that gives you vertical height with your initial speed, v naught, and your initial height, s naught. Okay, and now we derived it using calculus. We didn't have to have that memorized. Now, it helps if you're familiar with it, so you know what you're looking for.
Yeah,
but
one more question is like always the acceleration always just negative 32.
If you're dealing with feet per second, yes. If you're dealing with meters, it's negative 9.8.
Yes, that's what I mean. It's like in this question you got the acceleration is like negative 32 t plus something.
We found the speed was negative 32 t.
So what's the unit?
Why isn't that moving?
It's like
I mean in this question the acceleration. What is the number of what is the equation of the acceleration?
Acceleration is equal to negative 32. It's a constant.
Oh, okay.
Okay. All right. I'm not sure why this isn't moving. That's not good. Let me erase it. Where's the eraser? There we go. Okay. So that is the position function for this ball. We still need to go back and solve the question that it asks us about. Okay. Scrolling back up here. Yeah, this is where we wrote that acceleration is a constant. Okay. Oh, I wanted to make one note. You'll notice that when we found the speed, we ended up with this constant of acceleration. I'm sorry, this constant of integration c. And then later on, when we were finding position, we also called it c. Okay, it's important to keep in mind that c is like a chameleon. You know what a chameleon is? It's a lizard, right? It's a lizard that changes color so that it's the color of its surroundings. So it changes based on where it's at. We call both of them C, but that doesn't mean they're equal to the same thing. Okay? That's important to note. And if you didn't know what C was in this first equation, you would need to give it some indication. So like C1, you could call it. And then you could continue to integrate, you just wouldn't know what that constant was. Okay? All right, so solving our second question, when does the ball hit the ground? Okay, so our question is, when is our position function equal to 0? Okay, so this is really an Algebra 2 question. Okay, one way to do it is to factor. Right? First we can factor out a negative 16, and then we're left with
minus 4t plus minus 5.
okay, and then we can factor that, which is negative 16 t plus 1 t minus 5. So our solutions are t equals negative 1 and t equals 5. Okay, which one's correct?
5.
Only the positive one. Right? Time can't be negative. Okay, so our solution is that the ball hits the ground 5 seconds after it's thrown.
That's a good question.
Okay, good, because you're going to do some for practice. All right, that's it for 4.1. And we'll do some practice.